Hey, Chem 20s, our lesson tonight is going to be on ionic compounds, meaning instead of talking about the intermolecular forces that are there for a molecular compound, we are going to look at the intermolecular force that is there for an ionic compound, and that is ionic bonding. So, all ionic compounds we know form a crystal lattice. We have talked about this for so long, but I want us to get a better understanding of this crystal lattice. So, I've got a few. We have our crystal lattice here, NaCl. Again, you've seen this probably before, especially if I've had you. I have a different crystal lattice right here, still set up pretty well the same. Okay, again, it's alternating our positive cation with our negative anion, depending which one's which on which crystal lattice we grab, which compound we grab. Again, when we go to build one of these, we are mixing in lowest, simplest number ratios, cations and anions. We're going to call this interaction an ion-ion interaction. So when we're dealing with ionic compounds, we are dealing with ion-ion interactions. And the reason we call it that is because we have this large network of charged particles. And so we have the positive cation, the negative anion, and we build this lattice like in the picture here. So here is NaCl. We've zoomed in. Here's what the crystallized structure looks like when you zoom in. Here's what we're seeing when we look at these alternating positives and negative bonds. This is the strongest intermolecular force because this intermolecular force has something that the other ones do not have. They have actual formal charges. In molecular compounds, because they were sharing, remember the forces were induced. Well, in an ionic compound, because we are gaining or losing, we're giving away, there is this actual formal part of this charge. These are the strongest intermolecular force. Well, let's take a look at an example that we've honestly looked at probably a zillion times by now, and that is we're going to look at NaCl. I want us to remember that in an ionic compound, we transfer electrons. The metal or the cation is always the one that loses electrons. Because remember what happens in its outer shell, it would rather lose one than, let's say, in sodium gain 7. So it loses to get to that noble gas configuration. In chlorine, chlorine would rather gain one than try to lose 7 to get to that noble gas configuration. Therefore, by gaining an extra electron, it has one more electron than protons. It's got that negative charge. That's what turns it into an anion. The key to building these crystallized structures are, again, because it's an ionic compound, we are going for a net charge of 0. There is going to be neutrality or neutral overall on this crystal. Now, this can be anything from something simple like NaCl, or again, something a little bit more complicated like using polyatomic species like ammonium carbonate, where we have an ammonium cation and we have a carbonate anion. And they can get actually to be quite difficult when you look at the structures. Now, here's the NaCl you know, you love, you're used to. Okay, they have some what we like to call the nearest neighbors. Now, this is probably for 30 seconds going to go farther than we need to in high school, but I want you to see this. So I have this other model kit, and unlike the model kit we use in class, this one's a little bit better for this. You'll notice that my center guy here, he can make 6 bonds. And really what I wanted to do was I built this. I didn't care what colors I grabbed. I wanted you to see that it doesn't matter if I put the cation in the middle or the anion in the middle, sodium or the chlorine. This substance is going to have 6 neighbors, left, right, forward, back, up, down. In this crystallized structure, every single charged ion has 6 neighbors with the opposite charge. So if I think about this middle guy as sodium ion, Na positive, he's got 6 chloride ions covering on each 6 sides of him. And then this chloride ion would then have 6 sodiums on each side of him. And this is how the shape builds itself out to make this crystalline 3D structure. Now, the part that's the most important for us right now in this course is I want us to be able to represent how we form ionic compounds using electron dot diagrams. We have done a very good job at this for doing molecular compounds. We have spent 2 weeks pushing them together, drawing Lewis dot, then drawing stereochemical, then looking at intermolecular forces. Well, we need to spend a few minutes looking at ionic compounds. And so, again, when we go to draw these, we are only going to be looking at the representative elements on the periodic table. We're going to stick to the easy ones. So when I go to draw sodium, sodium is in group 1, therefore it's got 1 valence electron. Chlorine, we've drawn it a billion times, is in group 17, therefore it has 7 valence electrons. But unlike molecular compounds where we would just push them together and they would share full octet, in ionic compounds, remember, these guys transfer electrons. So sodium is going to transfer 1 electron over to chlorine. So chlorine has a full valence shell. Sodium, by losing the 1, he's going to now be left with a full valence shell as well. So metals are always the ones that lose, hence why they have a positive charge. Nonmetals are always the elements that gain, hence why they have a negative charge. So when sodium gives away its electron, it's going to be 1 electron short, so that's where it picks up its positive charge. Chlorine gains that electron, and so it's got a full outer octet. And you'll see that we put these set of brackets around it so that we don't confuse the charge on chlorine that it gets by gaining that extra electron. It gets that extra negative charge with the dots on the electron dot diagram. So we always, when combining charges with dots, put a square set of brackets. Now, the neat thing about this is, before we ever started this example, I don't have my pen. I'm going to get a pen here really quick, everybody. So I should have my pen now. So before we started this example, if we were to prove sodium chloride, we already know the answer before we get to the end. Sodium has 1 positive, chlorine has 1 negative. Of course, they're going to cancel out. We need 1 of each. So we already knew before we started this question that we were going to make NaCl. There's no surprise for that for us. So what I would like us to do is, let's look at the next example, and I'm going to have you try it. So please pause the video. I would like you to take a second, and I would like you to draw the equation using electron dots for magnesium fluoride. Draw magnesium with the appropriate dots. Add to it fluoride with the appropriate dots, and see if you can figure out how we're going to make magnesium fluoride, because this one's going to be a little bit different. Pause the video now before I go through the answer. Okay, I gave you warning. So we're going to start with magnesium. Magnesium is in group 2, so it's going to have 1 dot, 2 dots. We're going to add it to fluorine. Fluorine is in group 17, so it's going to have 1, 2, 3, 4, 5, neighboring 6, 7. Now, fluorine's not happy because it doesn't have a full octet. Magnesium's not happy. So magnesium's going to go wee all the way over here and donate an electron. So now fluorine is going to be happy. But magnesium still isn't happy. So magnesium goes, well, I know there's another fluorine floating around. So there he is. So magnesium is going to donate its other electron all the way over to fluorine. Now magnesium is happy because it's lost 2 electrons. Fluorine is happy because they each gained 1 electron. And so when we are done, magnesium lost 2 electrons, which makes it 2 positive because it now has 2 more protons than it had electrons. Fluorine is happy because it's now got the full valence level or full octet. And because it filled up and it gained an extra electron, it now has a negative charge. And we have to draw this again because remember, we have 2 fluorines. Now, this should make sense to us because, again, I would say before we started the question, you knew the job was we were going to make magnesium fluoride. Well, magnesium has a 2 positive charge, fluorine has a 1 negative charge. So we were always going to need 2 fluorines. So before we started, you already knew that you were going to end up with that guy, because that was our prediction before we ever started. And we've been doing this for a very long time. Now, what I would like us to do is check our work. So I'm going to grab my arrow right here and let's drag out my answer. And we can see that, hey, we match up exactly right. Okay. Now, we're going to do one more example. This time, now that you know that we can do doubles and we can bring things as we need them, again, for me, the trick is you already know the outcome. Work your way to the outcome you already know for an ionic compound. So let's do the last example. Can you show me, please, how to represent, using an electron dot diagram, the formation of aluminum oxide? Pause the video now before I go through the answer. And again, I'm just going to pull up the answer. So I drew aluminum with 3 dots. I drew oxygen with 6 dots. Aluminum donates an electron. Aluminum donates another electron. Oxygen is happy, but aluminum still has an extra one. So we're going to draw another oxygen. He will donate his electron. Now aluminum's happy, but oxygen's not, still has an opening. So we're going to draw another aluminum. Aluminum donates again. Now oxygen's happy, but aluminum's not. So we have to draw another oxygen. And we go back and forth until everybody's happy, both the metal and the non-metal. When we are finished, 2 separate aluminums have donated 3 electrons each. 3 separate oxygens have gained 2 electrons each. And so when I take a look at this, again, this looks very familiar to me because, again, we already knew walking into this question how to write aluminum oxide. Aluminum has a 3 positive charge, oxygen has a 2 negative. Therefore, when we go to do this, we already knew when we went to form this, we are going to make Al2O3. I have no problem when you go to draw this out if you represent AlO23 and write this out, Al2O3, and if you write this out underneath what you just made, because that's, in my opinion, how you check your work. I hope you found Ionic quite easy. It's supposed to be. You come with a lot of background for Ionic. Good luck, and we're almost done the bonding chapter.